We've been using L'Hopital's rule to take the limit of indeterminate forms. But what really is an indeterminate form? How should I think about this? Let's look at some examples. Let's look at the limit as x approaches infinity of x squared plus 1 over x squared plus 4. We have seen how to calculate this limit before, but let's also notice that as x goes to infinity, the numerator is going to infinity, and the denominator is also going to infinity. So this is of type infinity over infinity, so we have an indeterminate form. That means we can use L'Hopital's rule, and in order to get some practice with it, we'll go ahead and use that on this problem. Now, a lot of people think that infinity over infinity, well, I have infinity on the top and I have infinity on the bottom, so shouldn't this just give me 1? Well, maybe. Let's see what happens when we take this limit. So, using L'Hopital's rule, so I'll put LH over the equal sign here to indicate that that's what I did. This is the same as the limit as x approaches infinity. Well, I take the derivative of the numerator, that's 2x plus 0, and the derivative of the denominator, that's 2x plus 0. Well, and 2x over 2x, limit as x goes to infinity, is just the limit of 1. So in fact, I do get 1 in this case. But is that always what happens? Let's look at another example. Now I have the limit as x approaches infinity of x squared plus 1 all over 2 times x squared plus 3. Again, I look at what happens as x goes to infinity. The top is going to infinity, the bottom is going to infinity. So this is again of type infinity over infinity. Do we still get the limit to be 1? Let's check it out. So using L'Hopital's rule, which we've already decided is allowed here, the limit as x approaches infinity is equal to, I take the derivative of the top, well, that's 2x plus 0, and the derivative of the bottom, well, in this case, I get 4x plus 0. So this is the limit as x approaches infinity of, well, 2x over 4x is just 1/2. So the limit in this case is 1/2. Okay, well, maybe this infinity over infinity is a little harder to understand than we thought. Let's look at another example. This one is the limit as x approaches infinity of x squared plus 1 over x plus 4. So again, the numerator is going to infinity as x approaches infinity, and so is the denominator. So this is still type infinity over infinity. That means I can use L'Hopital's rule. So let's do that. I get the limit as x approaches infinity. Well, the derivative of x squared plus 1 is still 2x, and the derivative of x plus 4 is 1. Well, so this is the limit as x approaches infinity of just 2x, and as x goes to infinity, 2x is still going to infinity. So the limit in this case is infinity. So I got 1, and I got 1/2, and I also got infinity. So maybe the natural question to ask is, can I write down a limit where the type is infinity over infinity, and the result is some number a, right? So any number a. I could pick a to be 5, I could pick a to be 10, I could pick a to be negative 756. Can I write down a limit where this is true? And the answer is yes. Let's do it. Well, if I think a lot about the things that I've just been doing here, it's not too surprising that if I look at the limit as x approaches infinity of a times x squared plus 1 all over x squared plus 1, well, what am I going to get? We first have to determine that this is the right type. So as x goes to infinity, a is a number, so the top is going to infinity. And as x goes to infinity, the bottom is also going to infinity. So this is still type infinity over infinity, which we want, which means we can use L'Hopital's rule. And we get that this is the same thing as the limit as x approaches infinity of, well, I take the derivative of the top, that's a times 2x, and the derivative of the bottom, 2x. So this is the limit as x approaches infinity of just a, which is a. How exciting is that? So here, I see that I can create a function that has any predetermined limit at all. So it looks like it should be infinity over infinity, and rather than being able to say that that's 1 or infinity or even maybe 0, I can create a problem where I get any value of a. The example that I did here is probably not very illuminating because it's a pretty easy example and we could have done this limit weeks ago. So I challenge you to try to find another type of function which is type infinity over infinity, and you can produce any limit at all. So with the indeterminate form infinity over infinity, we see that we can't really say anything about what the limit is knowing that it's infinity over infinity. We cannot determine it. What about the case when the indeterminate form is 0 over 0? What can we say then? Let's first look at the limit as x approaches 0 of e to the x minus 1 all over x. So as x is approaching 0, e to the 0 is 1, and 1 minus 1 is 0, so the numerator approaches 0, and the denominator approaches 0 as well. So this is definitely type 0 over 0. And again, like before, we might be tempted to think of 0 over 0 as somehow equaling 1. We could cancel those zeros or some kind of thing like this. But maybe after the last examples with infinity over infinity, we want to be a little more careful. So let's evaluate this limit and see what we get. All right, well, it's type 0 over 0, so I can go ahead and use L'Hopital's rule. So I get the limit as x approaches 0. I take the derivative of the top, e to the x minus 0. The derivative of the bottom, that's a 1. So this is the limit as x approaches 0 of just e to the x, and e to the x is continuous at 0. So I can just plug in 0 and I get e to the 0 equals 1. So in fact here I did get 1 for my limit, but again we have seen that we need to be cautious about this, so let's see another example. Limit as x approaches 0 of e to the x minus 1 minus x all over x squared. So as x approaches 0, I have e to the 0, which is 1 minus 1, so that's 0 minus 0 is still 0 on the top, and x squared as x approaches 0 also approaches 0, so this is still type 0 over 0. Okay, so I can use L'Hopital's rule on this problem. This gives me the limit as x approaches 0, the derivative of e to the x is e to the x, the derivative of 1 is 0, and the derivative of x is 1, all over the derivative of x squared is 2x. Well, I don't really know what to do with this limit, so I investigate again what happens as I get close to 0. Well, e to the 0 is still 1, so I have 0 on the top, and 2x goes to 0 as x goes to 0. So this part is still type 0 over 0, which means I can use L'Hopital's rule again. So I get the limit as x approaches 0, derivative of the top is e to the x, derivative of the bottom is 2. So this is the limit as x approaches 0 of 1/2 e to the x, or again, e to the x is continuous at 0, so 1/2 e to the 0, or just 1/2 times 1, or 1/2. So we got 1 as our limit, we got 1/2 as our limit. Let's see another example still. This one is maybe a little contrived, but we're using it to prove a point, so we'll do it anyway. Limit as x approaches infinity of x to the negative 1. Well, 1 over x goes to 0 as x goes to infinity, and e to the negative x also goes to 0 as x goes to infinity. So this one is still type 0 over 0. So I can use L'Hopital's rule. Limit as x approaches infinity. Well, I take the derivative of the top, that's negative 1 x to the negative 2, and the derivative of the bottom, e to the negative x. So let's do a little algebra here. Limit as x approaches infinity, negative 1 over negative 1 cancels, and x to the negative 2 is really like 1 over x squared, e to the negative x, right? And e to the negative x is really a lot like e to the x in the numerator, so this is the same thing as limit as x approaches infinity of e to the x over x squared, right? So here I have as limit as x approaches infinity, e to the x goes to infinity, and x squared goes to infinity. So I can use L'Hopital's rule again. This one is type infinity over infinity. So the derivative in the top is e to the x. The derivative in the bottom is 2x. Still type infinity over infinity. So I take the limit as x approaches infinity using L'Hopital's rule. Derivative of the top is e to the x. The derivative of the bottom is 2. And then we can see that as x goes to infinity, this thing goes to infinity and this thing goes to 2. So the limit is positive infinity right now. Could I just have done this here? Lots of algebra? Sure. But I wanted to see a type 0 over 0 problem that gave me infinity. Right, so I've gotten 1 for my answer, I've gotten 1/2 for my answer, I've gotten infinity for my answer. Again, I think that maybe I ask, can I write a limit of type 0 over 0, whose value is some number given number a. So again, a can be any number, and I basically want to show that this 0 over 0 type can have any answer at all. And the answer is still yes. You have to play around with this one a little bit more, but let's look at the limit as x approaches 0, building on some of our earlier examples, e to the ax minus 1 all over x. Well, as x goes to 0, e to the a times 0, 0, so this is e to the 0, which is 1, and 1 minus 1 is 0. And in the bottom, as x approaches 0, then x approaches 0. So this really is type 0 over 0. So I can use L'Hopital's rule, and I get the limit as x approaches 0, taking the derivative in the top, the derivative of e to the ax, using the chain rules, a e to the ax, derivative of 1 is 0, and the derivative of x is 1. So this is the limit as x approaches 0 of just a e to the ax. E to the ax is continuous, so this is a times e to the a 0. And a times 0 is 0, so this is really a e to the 0, which is just a times 1, or a. So again, I got that this 0 over 0 type limit can take on any value at all. As long as you give me this value a, I can create this limit and get a for my answer. I hope this has been a good chance for you to practice some more using L'Hopital's rule. Keep working on problems, keep up the good work, and good luck.